welcome back. So there's one more slide I want to share with you about point estimation. Then we're going to get into the sampling distribution of our point estimators and of a point estimate, X bar in particular, and we're going to see an example of that. And that can all sound like Greek, but hopefully at the end of this video it makes sense. So last thing I want to show, this is like really pretty self-evident, but hopefully it's a little bit helpful to some people. But this is just a basic kind of process of point estimation. So what is the population with some mean? You don't know what the population mean is. So you do a simple random sample of n elements that's selected from the population. And the sample data provides a value for the sample mean, right? So you get a sample mean. And the value of the sample mean is used to make inferences about the value of the population mean. So that's pretty straightforward. But you can pause the video, maybe that's helpful. All right, now we're going to talk, and this slide was actually categorized under the next stuff we're talking about, and I thought that really should belong with this, so I changed it. So now we're going to talk about sampling distribution, and we already mentioned this, but that when you do a sample, when you get a sample of a population, so here's your population, then you take a sample, let's say there's like 30,000 students on this one campus, and it's a finite population, you have a list of 30,000 students, so you do a simple random sample where you're going to select 30 students and study them. And so you assign a random number to all the students, and then you sort them from least to greatest. And you take like the 30 smallest random numbers and you study those students. Randomly selected students from the population. And when you do that, you do this one sort of like study to get some data, you get a sample mean. And that sample mean is going to make inferences about the population mean. Right? So let's say it's height, and we did this example before, and you find out that everybody out of the 30, the average height is 6'1", for whatever reason. And then you do the sample again, right? You do another one, you get another 30 students, and the average height is 5'6". And you do the sample again, and the average height is 5'8". And so every time you do a sample, right, your point estimator, the sample mean, which is going to estimate the population mean, that sample mean will be different. It'll be different based upon the sample. It'll vary slightly. How much is it varying, and how closely does it approximate the population mean? That's the question. How much is the sample, the statistic, the sample point estimator that we're going to use to make inferences about the population, how much is that varying around the true population parameter? The word parameter is used to describe the parameter that we're interested in, the characteristic of interest for the population. When you talk about a population, it's the parameter, right? So the parameter we're interested in, the characteristic we're interested in is the average height, and that's for the population. How much is the sample, the sample point estimator of the population parameter, the mean? How much is the sample point estimator, the sample mean, accurately getting close to the population mean? Well, the larger your sample, the more you're going to get closer, right? The closer you're going to get. You're going to have less deviation in those samples. The larger the sample metric, the sample point estimator of the population parameter, you're going to have less variance. If you survey all 30,000 students, right? You're doing a census. And then your data that you collect is going to accurately reflect that population. Well, let's say your sample is 29,999 students. You don't do the whole population. You do it all except one. Like with 29,999 students, you're going to get a really close estimate of the population. Your sample is, well, what if you did 20,000 students? You're going to get a close estimation of the population with your sample. What if you did 10,000 students, 5,000, 3,000, 2,000? You're still going to get a really close estimate with your sample, a really close estimate of the population. Your sample point estimator of the population parameter, we're talking about the mean, the average here of height, as in our example, that with 2,000 students, a sample of 2,000 students out of 30,000, you're going to get a really close approximation. What if you did 50 students? You're still going to get a pretty close approximation, right, of the population parameter with your sample point estimator. What if you did 30 students? It's still going to be a close approximation of the population parameter. Your sample point estimator is going to be a close approximation of the population parameter, the mean, right? The parameter we're looking at in this, the characteristic of interest that we're looking at here, is the mean for the population. That's the parameter for the mean. What if you did 20 students? Now you're going to start to have more variance in your mean. And so we could do a whole bunch of samples with, you know, a smaller number in each sample, and we're going to get a distribution of what that you know, so we do our sample, let's say with 20 students, let's say with 30 students, and we're going to get one value for x bar, for the sample mean. Remember, x bar here is the sample mean, and that's going to estimate the population parameter, the mean of the population, right? The sample mean will be a point estimator for the population mean, which is known as a parameter in the population. And so if we like do one sample, we might get 6 foot with 30 students, and we do another one, we might get 5'6". We do another one, we get 5'8". Well, we're going to get, like if we did a whole bunch, we're going to get a distribution of, you know, sampling distribution of the different values that our sample mean could be. And so that's what we're going to learn about in this video. So let's go through the slides. And by the way, this idea that the larger our sample size, the more the sample point estimator is going to accurately reflect the population parameter, the characteristic of interest that we're interested in for the population, right? The sample point estimator is going to more accurately predict, you know, align with, and, you know, determine the exact population parameter, the mean, when we have a larger sample. So the central limit theorem says when the population from which we are selecting a random sample does not have a normal distribution, the central limit theorem is helpful in identifying the shape of the sampling distribution of, we're talking about x bar, the mean here, the sample mean, in all these examples that are yellow. But the central limit theorem says in selecting random samples of size n from a population, the sampling distribution of the sample mean x bar, the mean, the sample mean, can be approximated by normal distribution as the sample size becomes large. So the larger the sample size becomes, right, the closer we're going to estimate the population mean, the population parameter that we're interested in. And we're going to get a normal distribution for the many different values that our sample mean could take on. We're going to have a normal distribution. And that normal distribution is going to allow us to use some of the stuff we've already learned about bell curves and the normally distributed data, right? The normal distribution. So here we're looking at the sampling distribution. What is the distribution? And in this example, it's of our mean. So I could put up here sampling distribution of the mean, right? And on the rest of these, same thing, okay? Sampling distribution of the mean. But what is the sampling distribution of the sample? I should put sample mean. Of the sample mean. Sample of the sample mean. The sampling distribution of the sample mean is the probability distribution. It's a probability distribution, you know, and it's going to be normally distributed if it's coming from data that's normally distributed. So it's the probability distribution of all possible values of the sample mean x bar. And the expected value of the sample mean, should be the population mean, right? And when the expected value of the point, and again, just our notation here, sample mean, population mean, when the expected value of the point estimator equals, the point estimator being our sample mean, when the expected value of the point estimator equals the population parameter, so we use parameter to talk about the characteristic of interest in the population, we say the point estimator is unbiased. All right, whatever. Yeah, of course it's unbiased. You know, the sample matched the population, so it worked. Sampling distribution. We will use the following notations to define the standard deviation of the sampling distribution of the sample mean. So notice this is like we're looking at the sampling distribution. We're looking at the sampling distribution of the sample mean, right? So now, before we had random variables and we got different, you know, distributions for those random variables, and we were able to do some probability based upon that. We learned about the normal curve and how we could find the z-score and figure out what percentage of data under the area of the normally distributed curve would be to the left of that z-score. So we could start to do some probability stuff, right? And now we're doing that same thing. We will use the following, we're doing that same thing with our data from the sample. And so there's a sampling distribution of the sample mean, meaning we could have 6 foot with one sample, we could have 5, 6 with another sample, we could have 5, 8 with another sample, and all those possible values are going to create a sampling distribution of the many different values of the mean. So it's like our sampling distribution becomes a random variable, and it could take on different amounts. The x bar, the sample mean, could take on different amounts. And then we could do statistics on that. We could do statistics on our statistics. Gets a little bit like, what's that movie where it's reality within reality? Inflection or something like that. So here we have the standard deviation of the sample means. And that notation is standard deviation with a lower, what's that? Raised to the power, I don't know what that's called there, with a lower x bar there. And then we have a standard deviation of the population. And so that's the standard deviation of the population right here, right? And it comes from taking the square root of the variance. And then we have the sample size, and we have the population size. So that's like just notation that we're going to use. And we have these formulas we could work with to get the standard deviation of our sample mean. So if it's a finite population and we're using, a sample, right? So there's two formulas: finite population and infinite population. And in a finite population is treated as being infinite if n, small n over big N, is less than or equal to 0.05, right? And so if we have 100 people, let's say we have 1,000 people here in our population, and we survey 30 of them. 30 out of 1,000, if we were to do the math on that, 30 out of 1,000, calculator, 30 divided by 1,000 is equal to 0.03. That's smaller than 0.05. I did 30, my small n, out of 1,000, my big N, my population, my sample size is the small n, 30, out of my population is 1,000. And so we have 0.03, which is less than 0.05. And when you have this situation, because the people who created this got PhDs in it, and they just do that for their life, this math, and so we're just going to take that on face value. When you have this situation, you could treat a finite population as infinite, and so you don't need this finite population correction factor here, okay? And so, for all intents and purposes in this introductory course, all of the things we do are just going to be less than 0.05. The sample size, the proportion of the sample size to the population will be less than 0.05. So we could treat it as infinite and just use this. And we don't have to worry about this formula. And the standard deviation of the sample statistic, the sample mean in this situation, is referred to as the standard error of the mean. Okay, so this is a standard error. Then we call this the standard error. It's standard deviation, but it's a specific kind of standard deviation. It's the standard deviation of the sample mean. Okay, so you got to wrap your head around that. What is that movie? What is the movie with reality in reality inflection or something like that? It begins with an I. And this is not a Google question. I will just get nonsense. If I ask that of Google, I'm going to put it into ChatGPT. It's, I'll be amazed. Reality. It sounds like, oh, it's not reality. That's not what I'm looking at. It is, it had, hold on. I got to go find this. Hold on. I love ChatGPT, right? So I'm like, no, it's the movie with the spinning top at the end. And it's like, oh, you're thinking of Inception by Christopher Nolan. Amazing. Totally amazing. So incredible. So it's kind of like reality within reality, statistics on our statistics. So that's standard error of the mean, okay? It's the standard deviation of the sample mean, right, that we're doing. And we're talking here, remember, we're doing sampling distribution of the sample mean. Sampling distribution of the sample mean. Sampling distribution of the sample mean. So when the population has a normal distribution, the sampling distribution of the sample mean is normally distributed for any sample size. Good news, because we like normal distribution in statistics. In most applications, the sampling distribution of the sample mean can be approximated by a normal distribution whenever the sample size is 30 or more. So what this tells you as a statistician, right, is that when you do a sample, you want to do a sample where it's at least 30. Because if you do 30, you're going to approximate the normal distribution, even if your population doesn't have a normal distribution. And you need to also keep, like this, your sample size, right? 30 out of like 1,000 is great because you get 0.03. But if that got greater than 0.05, you would need to do this, okay? You would need to do that, okay, to calculate your standard error. And this is such an important phrase, and it's so important to remember that standard error, I'm going to make it green, okay? It's such an important phrase. And I'm going to bold it. Here we go. You ready? I'm going to bold it. I'm going to tell you everything I'm doing. I'm just going to narrate my whole life, all my actions, all my thoughts. The standard error, you're going to see this, and you just want to remember standard error is the standard deviation of the sample mean. Okay, standard error is just the standard deviation of the sample mean. We have all these different sample means. We have a total distribution of our sample means. It's our sampling distribution, and when we look at all the possible data, that's that it could be, that's a random variable. It could be this one. It could be this one. It could be this one randomly. And when we looked at all that possible data, we could calculate statistics on that data: mean, median, mode, variance, standard deviation, like all of that stuff. And standard deviation, and so just as a reminder, right, here we have mean, variance, standard deviation, so we could calculate those. And the standard deviation of our sample mean is the standard error. So you just have to remember that, standard error, because you're going to see that. And if you don't ingrain it in your head, that standard error is just standard deviation for the sample mean, you're going to be like, what's standard error again? As you're reading the textbook. So you want to have 30 or more, and in cases where the population is highly skewed or outliers are present, samples of sizes 50 or more may be needed. And let's just keep this. I like this description here. So we're going to keep that, and we're going to go here and put that there. Sampling distribution of the sample mean can be used to provide probability information, because we have sampling distribution, and we could start to use our z-score stuff. So z-score table, there we go. And if we look at this, so here's the one we looked at last time, we can start to use our z-score. We have a normal distribution, and we can start to use our z-score to say, hey, this much data is from this point over to the left. And what is z? Remember, z is the difference between a data point and the mean divided by the standard deviation. So, if I had like 3, I'm just going to do proportions here for a moment. If I had 30, just doing proportions, if I had 30 out of 100, that's 0.3 or 30%. If I had 50 out of 100, that's 0.5 or this is crazy. It's 0.5 or 50%. If I had 88 out of 100, that's 0.88 or 88%. If I had 88 out of 200, that's 0.44 or 44%, right? If I had 3 out of 4, that's 0.75 or 75%. And so, you have your numerator and you have your denominator, and this is how proportions work. And so if I have the distance of a point from my mean here, and I divide that by my standard deviation, it's going to show me a proportion of my standard deviation, right? Just like 3 out of 4 would show me it's 0.75, right? And if that was like, if my point was 3, my point z, the formula for z, so let me just show you the formula for z. Let me go get it. Hold on. Okay, here's my formula for z, my z-score. And z shows the distance from any data point, xi, to the mean, right? The distance from the mean of any data point divided by the sample standard deviation, right? So the standard deviation down here. So if my standard deviation is 4 and the distance of some data point from the mean is 3, I'm going to have a z-score of 0.75, which means it's like 0.75 of my standard deviations. And so when you know your z-score, with your z-score, you could start to use and if it's normally distributed, you could start to use this z-table. And the z-table will tell you from this point here, this z-score over there, this percentage of your data is from here to the left. And so when you have a distribution of data like that, where it's normally distributed, you could use the z-score, then you can start to calculate the probability. The sampling distribution of the sample mean can be used to provide probability information about how close the sample mean is to the population mean. And I know that all might sound like gibberish if this is the first time. We're going to see an example coming up, and hopefully that'll clarify it for you. All right, so again, I'm going to copy this because I'm liking that one, and I'm going to bring this down here, and oops, just bye. Put that one in there. When the population from which we are selecting a random sample, we already read this, I'll read it again, does not have a normal distribution, the central limit theorem is helpful in identifying the shape of the sampling distribution of the sample mean. The central limit theorem says in selecting random samples of size n from a population, the sampling distribution of the sample mean can be approximated by a normal distribution as the sample size becomes large. And we saw what that approximation is like 30 or more. Okay, 30 or more, or if it's skewed, 50 or more. So and I think this would actually go better like this. Like read about it there, and then like here it is, and then we're talking about probability, and now here's the probability. I don't know who puts these presentations together. The textbook did not do the greatest of jobs, I'm telling you. All right, so good. I'm improving it for the way I like talking about it. Here we have an example. So note. The sample size out of the population, we have 30 out of 2,500, so that's 0.012. And because that's 0.012, which is less than 0.05, we can use the infinite population and not worry about this little, whatever, finite population correction factor. Okay, so because sample size is less than 5% of the population size, we ignore the finite population correction factor. Good. Here's the scenario. Suppose the personnel director believes the sample mean, right? Sample mean will be an acceptable estimate of the population mean if the sample mean is within $500 of the population mean. Okay? What is the probability that the sample mean computed using a simple random sample of 30 employees will be within $500 of the population mean? And so here's the data that we're given. Sampling distribution of our sample mean. Here's our sample mean, 71,800. And that is our expected value, right? And our expected value should be the population mean. Expected value of X should be the population mean. But that's our expected value, right, for the sample. That's what we're shooting for. This is a little bit weird to me, the way they say this. It's like, hey, the sampling distribution of the sample mean is the probability distribution of all possible values of the sample mean. The expected value, and so maybe this is like different, right? Maybe this is different. We'll just put this as different. And the expected value of the sample mean is the population mean. When the expected value of the point estimator, the sample mean, equals the population parameter, we say the point estimator is unbiased. Okay, whatever. So here we have our sample mean. And then here we have our standard error. What is the standard error? Pause the video. Answer that question. What is the standard error? You do it? All right, I'm just making sure I'm recording. The standard error is the standard deviation of the sample mean. Okay? The standard error is the standard deviation of the sample mean. And that is equal to this. And where do we get that? It's right here. With an infinite population, the standard error is the standard error is the standard deviation of the sample mean. And we get that by doing the standard deviation of the sample. The standard deviation, no, that's the standard deviation of the population. Oh, well, it's right there too. Standard deviation of the population is right here, right there, okay? And it's also right here, standard deviation of the population. Let me just show you that again, right there, standard deviation of the population right there. So that's how we calculate the standard error, which is the standard deviation of the sample mean. And so here is the sample mean. Here we're calculating the standard error, the standard deviation of the sample mean. And we have $4,000 as our population standard deviation, or 4,000 is the population standard deviation. And our sample size is 30, so we have square root of 30 there because that's the formula. There's the formula. And we get 730.3 as the standard error, or the standard deviation of the sample mean, 730.3. What does that mean? Okay, what does that mean here? Well, we could say we want to know how much is within 500, our boss, the personnel director, will think the sample mean is an acceptable estimate of the population mean if the sample mean is within 500 of the population mean. So what that tells us is that right here, text, right? 71,800 plus 500 is equal to 72,300, and 71,800 minus 500 is equal to, just wondering, like plus takes up more room, I guess, equal to, and I don't know what it'd look like if I did it like this, if it's still going to be, there we go, that's better. And can we move that one over a little bit? It's just weird either way. And that's going to be equal to 71,300, 71,300. And I'm just going to make this all just a touch smaller, just to de-emphasize it. There we go. Bring this over. And I will put this like right here. And I'll make that a little bit smaller. And bring that down to like 14. And does that fit well? I kind of like that. That works. So 71,800 plus 500 takes us 72,300 and 71,300 down here. So the sample mean, if it's somewhere in that range from 72,300 to 71,300, right? So if our sample mean is somewhere between 71,300 and 72,300, and the population mean is also that, then the sample mean will be an acceptable estimate of the population. What's the probability that the sample mean computed using a simple random sample of 30 employees will be within $500 of the population mean? What's that probability? So to calculate that and figure that out, we get our z-score. And our z-score, so let me get these values here and bring this over so we could remember this. Boom, put this here, boom. Our z-score is 72,300 minus 71,800 divided by 730.3, right? So that's the upper endpoint of the interval. It's going to be up here. We're going to find our z-score. We have the value 72,300, but the z-score, and z-score, what is z-score? It's a point, that value, minus the mean divided by the standard deviation, okay? The standard deviation, the S, standard deviation right there of the sample. And so here we have standard deviation is 730.3 for the sample. That's the standard error, which is the standard deviation of our sample mean. And so we find from this point to the mean, we're using this formula, the z-score, from this point to the mean, get that value, divide it by the standard error, the standard deviation of the sample mean, we get 0.68. When we have 0.68, we could go here, right? That's our z-score. And 0.68, we're going to find the area under the curve to the left of the upper endpoint. So 0.68, and we come here and look at our z-score. 0.68 is right here, and it's 75.7517. So 75.17% of our data is from this point here, 72,300, to the left, right? That's 75.17% of our data. So there's the z-score table again. And then here we say from 71,300 to 71,800, we get a negative 0.68. So we go look up negative 0.68, and we have negative 0.68, which is right here, 0.2483. So, you know, from this point, 71,300, that value, which gives us a z-score of negative 0.68, right? 24.83% of our data is from this point over. So if we want to know the probability that we're here to here, we take this big value, which is 75.17%, 75.17%, and we subtract, because that's from here all the way over, from here all the way over, right? All the way. And then we subtract this, which is this part, and then we're just left with the stuff between them. So 75.17 minus 24.83, and we have 50.34. So remember, our question is, what is the probability that the sample mean computed using a simple random sample of 30 employees will be within $500 of the mean? And here's a picture of that, right? And the probability is 50.34%. a little bit like I don't get it because I didn't do the high-level PhD math to make all that happen. I mean, I understand how to do it, but it's also a little bit like you just have to take it on face value that this is how you do this stuff. And this is how you do this stuff, right? People taught me, and now I'm teaching you, and then that's how you do it. And I got to replace all these to make them the sampling distribution of the mean, because that's what we're doing here, people. We're exploring the sampling. Oh, that's not what I wanted. Sampling distribution of the mean. All right, so that's, well, I'll replace these with you at the same time just because it only takes a moment. There we go, we're almost done. We got two more. Sampling distribution of the sample mean. All right, so that's pretty cool, man. You learned about like the sample and the population, and we make inferences about the population by just, you know, getting data from a sample. And the sample has point estimators, which estimate the population parameters. And we looked at the sample mean to do that. And that sample mean could be treated as a random variable, which could take randomly that variable could randomly take on different values. And there's a distribution of those different possible values that sample point estimator could take on, the sample mean, right? There's a distribution of that. And then we learned a little bit about some of the properties of that distribution. And we saw that, you know, if it comes from a normally distributed population, then it'll be normally distributed. But if it doesn't come from a normally distributed population, then if you have 30 or more, it approximates a normal distribution. And the Central Limit Theorem talked to that. And then we saw that, you know, if we have less than 0.05 of our data, we could just use, like if the sample, right, is less than 0.05 of the population, less than or equal to, we can use the infinite population formula without the finite population correction factor, this stuff. We could use this formula to find out our standard error, which is the standard deviation of the sample mean. And then when we have our standard deviation of the sample mean, we could have a situation like this, where we have the sample mean that our sample came up with, 78,100, and then we could just arbitrarily say, what's the percentage of probability that the population parameter, right, the population mean is going to be within $500 of our sample mean. And so we could calculate our z value with, here is the standard deviation of the population, 4,000, that's just given to us. And then standard deviation, that's the standard deviation of the sample, that notation. Or no, that's standard deviation of the population, that's correct, sigma, right? Standard deviation of the population is sigma, right there. There it is, here, I'll draw around it. There it is, Control Z to undo that. And so we get our standard error, which is our standard deviation of the sample mean. And with that, we can then start to do our z calculations, because z requires us to take a data point and subtract it from the mean and then divide it by the standard deviations. Well, in this case, the standard deviations, when we do that, the standard deviation we're using is the standard deviation of the sample mean, which is the standard error. And so we find the difference between the data point, 72,300, the data point xi right here, right? And then the mean, we find the difference between that, and we divide it by the standard deviation of the sample here, like that. But this is the standard error because we're doing the sample. We're doing the z-score for the sampling distribution of like our sample mean. So we use standard error, and then we get that z-score. And when we have that z-score, we can start to say, all right, from this point here, 72,300, 75.1% of our data is going to be from here to the left. And then we could do that with the other point, 71,300, right, where we're over here. And we get this, and we say 50.34% of our data is going to be in here. And we have a 50.34% that this is going to be within $500 of the population mean. That's how that works. All right, so that's sampling distribution of the sample mean. It's kind of interesting. I hope that made sense. Watch it again, do some problems. You could go to ChatGPT and ask ChatGPT to give you problems, and you can work it to help reinforce it and ask ChatGPT for explanations. All right, see you in the next video.